Hello, this is Mrs. Taylor, and I'm going to introduce you to the law of exponential change. And in order to understand that law, you need to understand exponential growth. And exponential growth is growth in which the rate of change is proportional to the amount present. So a really good example of this is bacteria. The growth rate of bacteria is proportional to the amount of bacteria you have. So if you think about it, the more bacteria you have present, the more bacteria that will be produced through reproduction. And so with each new generation of bacteria, your rate of change changes because you have a new amount that is reproducing. So exponential growth is the change when the rate of change is proportional to the amount present. And so our differential equation that models this growth is dy over dt equals ky. And so remember, dy over dt represents your rate of change with respect to time, and k is what we call the either growth constant if it's positive or the decay constant if it's negative. So if we take our model and we solve it, solving it as a differential equation, which just means that we integrate, we get a model of exponential growth that may be more familiar. So in order to solve, we use separation of variables, where we move our y over to the side with the dy and we move dt to the right, and so the result would be an equation that looks like this. And then from there we would want to integrate both sides, and you may recognize the left side as an integrand for a natural log, and then on the right, remember k is a constant, it's just a number. So when I integrate with respect to t, my variable that I get as a result is t. And so when I integrate to solve the differential equation, I get this. The natural log of y, the natural log of the absolute value of y is equal to kt plus c. And from there, when we solve a differential equation, we want to solve it explicitly, which means get y by itself. And so in order to do that, I would raise both sides as the exponent of e and then simplify. So it would look like this. Your first step would be to raise both sides as exponent of e. The left side, your e to the natural log, would cancel and you'd be left with the absolute value of y. And on the right side, this is like what we've been doing with separation of variables, where if you're adding the exponents, it's the same as multiplying like bases. And so through simplification, you end up with this. The absolute value of y equals e to the kt times e to the c, and e to the c would just equal another constant. So typically we don't write e to the c, we just make that a c to represent that it's a constant. So your model would just become c times e to the kt. And then on the left side with the absolute value bars, if you think about it, e is a positive number. So if I raise it to any exponent, my result would be positive, so I don't need the absolute value bar. So your resulting solution to the differential equation is y equals c times e to the kt. And you may have seen this in several different situations. One of the most popular is for profit, and so it's PERT, so y equals p times e to the rt. But it's all the same model, it's just using different variables. And so this is our general model for exponential growth or decay, depending on the k value. And so that brings us to the law of exponential change, which states if y changes at a rate proportional to the amount present, that is, if dy over dt equals ky, so remember k is your constant for growth or decay. And so if that's the case, and y equals y sub 0 and t equals 0, it's just saying your initial value, then y equals y sub 0 times e to the kt. So this is basically what we just wrote, but instead of writing c, they write y sub 0. And the reason they do that is it's more clearly communicated that this constant is an initial value. So at the start, when t equals 0, we're representing our c, our constant, our coefficient, as y sub 0. And so the constant k is called the growth constant. In general, we don't really call it the decay constant. It's called the growth constant if k is greater than 0, or the decay constant if k is less than 0. So that's the law of exponential change. Well, how does that help us solve a problem? So let's say our setup for our problem is the rate of change of y is proportional to y. And so that's the key phrase that you are going to look for in these problems, is that rate of change is proportional to whatever your situation is. So the rate of change of y is proportional to y. The rate of change of the growth of the bacteria is proportional to the number of bacteria. It all means the same thing. And so when you see that phrase, you can call to mind the model that we just created. And that model is y equals c times e to the kt. And so you're going to use that in order to represent your relationship, and then use it also to find the value they're asking for. So they give you a bunch of values. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? And so this first phrase tells you that you are going to be using y equals c times e to the k t. And then from there, you are just going to use these ordered pairs to find the other constants that you need to model your situation. So when t equals 0, y equals 2. So if I plug 0 in for 0 in for t and 2 in for y, I get this. And if you think about it, when t is 0, this whole exponent becomes 0. Anything raised to 0 power is 1. So now I know that my c, my initial amount, my y sub 0, is 2. And so I can rewrite my model as y equals 2 times e to the k t. So that's the first step, your initial value. Find your y sub 0 or your c. The next step is to find your constant of proportionality. So that's your k, your growth or your decay constant. And in general, we call it constant of proportionality. So if I were to rewrite it as a differential, it would be that constant that represents the proportional growth. And so you use the second set of information to do that. When t equals 2, y equals 4. So plug 2 in for t, 4 in for y, and solve. Our next step would be to solve for k, our constant of proportionality. So I divide both sides by 2. 2 equals e to the 2k. And then to isolate k, I need to get rid of this e, and I do that by taking the natural log of both sides. So the natural log of 2 equals the natural log of e to the 2k. And the natural log and e would eliminate each other, and it would be natural log of 2 equals 2k, divide. And your constant of proportionality would be natural log of 2 over 2. And so once I put that into my model for exponential growth, I get y equals, we're using this here, 2e, and instead of k, now I know what k equals, the natural log of 2 over 2 times t. Now, this would be considered my model for exponential growth. Once I have values plugged in for everything except for y and t, I now have a growth model that gives me my population in terms of time. So at any time, I'll know what the population is. So the last question is, what is the value of y when t equals 3? All I would need to do is plug 3 in for t. So 2e to the natural log of 2 over 2 times 3. And then I would put that in my calculator and evaluate it to get the actual value. And so that is how I would use exponential growth to solve problems using the law of exponential change.